Okay, so let's kick off our GRAPHERGIA's sixth scientific webinar. And today our topic is dedicated to high-performance flexible micro-supercapacitors and advanced self-healing battery technologies. So a warm welcome to all of the participants and our speakers. I'm Mona Maril. I'm the communication and dissemination leader in the GRAPHERGIA project, and happy to have you all here for this 1.5 hour session to discuss these technologies. So today we will start with an introduction and the context to this session by the researcher who is involved in the supercapacitors work within the GRAPHERGIA project, Dr. Apurba Ray from German Aerospace Center. Then he will pass the floor to our first guest speaker, Dr. Boukherroub from the Institute of Electronics, Microelectronics and Nanotechnology in CNRS from France, who will talk about the high-performance flexible micro-supercapacitors for a 40-minute session. And then after his presentation, we will have a second guest speaker from the PHOENIX EU project dedicated to advanced self-healing battery technologies. And this presentation is given by Dr. Dermenci from Electromobility Research Centre at the University in Brussels. And at the end, we will have a question and answer session for 10 minutes. So before we kick off, I would like to warmly welcome all the attendees today. We have people from Europe, since this session is proposed by 2 European projects from GRAPHERGIA and from PHOENIX, but also well beyond. We have a great interest, I can see, for instance, in India. So maybe people are working also a lot in these countries dealing with these topics. And of course, the majority of you participants come today from the scientific community, but we have a bit of people also from e-textile and battery producer industries, which are the target stakeholders within the GRAPHERGIA, and also other research projects that are featured here. GRAPHERGIA is part of the Graphene Flagship Initiative, where we have these sister projects named here below, so Safari, Beyonce, and ARMS. So they are all dealing with the same topics, so welcome to you all as well. And with this, before I pass the floor to Dr. Ray, I would just like to remind you that this session is recorded, and we will share the recording in our communication channels afterwards. You can use the question and answer box during the presentations if you want to ask any questions in real time, and of course we will then take them after the presentations. And this session is proposed by our own GRAPHERGIA Hub, which connects researchers in Europe and beyond in the fields of advanced material technologies, battery technologies, and smart textiles. So I all thank you for accepting the invitation to follow our future activities within the hub. This is something that Apurba, you will mention later on. So let me just basically pass the floor to you, Dr. Ray. Thank you.
Okay, then I can share my screen now. Can you see my screen now?
It's coming. I'll tell you yes. Thank you.
Okay, so thank you so much, Mona, for this wonderful introduction and for kicking off today's webinar. And good morning, good afternoon to everyone in our audience. And thank you very much for joining our GRAPHERGIA Hub webinar. Today we are excited to dive into the high performance flexible micro supercapacitor and advanced self-healing battery technologies. And this project GRAPHERGIA is proudly supported by the European Union under the Graphene Flagship Initiative. So I am Dr. Apurba Ray, working as a research scientist at Institute of Frontier Materials on Earth and in Space. And today, I'm really excited to introduce about the GRAPHERGIA. The title of the GRAPHERGIA project is Innovative Pilot Lines for Sustainable Graphene-Based Flexible and Structural Energy Harvesting and Storage Devices. starting in October 2023. It is a 3.5 years initiative, brings 11 renowned partners across 6 countries. Our main focus, core focus, is to develop and integrate advanced graphene material into the next generation energy devices. Actually, we are paving the way for scalable, eco-friendly production of smart textile and next generation lithium-ion batteries electrode. And this GRAPHERGIA unites European innovators to unlock the potential of laser-assisted graphene production, shaping the future of self-charging, smart textile, and lithium-ion batteries. Because our mission is to integrate the energy harvesting into the everyday clothing, making a charge as you go a lifestyle a reality for everyone. To achieve this, GRAPHERGIA will develop and demonstrate a novel eco-design driven pilot scale process for the green production of uh, graphene and graphene related material. This sustainable 2D approach for 2D materials will power next generation energy storage, energy harvester, and conversion systems. And finally, and to translate the advanced research into real life applications. Ultimately, GRAPHERGIA will pilot its key exploitable result across three distinct demonstrations. That all-in-one self-charging textile capable of energy harvesting and storage, cell power structurally integrated sensor for aerospace structures, and advanced graphene-based lithium and batteries module prototype for space applications. And this GRAPHERGIA brings 11 research and industry partners for this project work, and this under the some coordination of Foundation for Technology and this Research and Technology Hellas, fourth in Greece partner, and all the consortium is oriented in the two main innovations. In this framework, DLR is mainly responsible for the development of high voltage gel polymer electrolyte in fabricating the flexible micro-supercapacitor, integrating those high voltage electrolyte and their details electrochemical characterization, and actively contribute to the demo 1 and demo 2. And the core approach of the GRAPHERGIA relies on the three distinct pillars. I would say there's laser-induced graphene electrodes, and this graphene to using this dry processing or one step processing that totally eliminate this chemical or any other Hertzsprung chemical reduction process, and this high voltage gel polymer electrolyte that eliminate the leakage problem and this flammability problem for traditional uh, aqueous electrolyte or liquid electrolyte, and finally the all-in-one energy harvesting and storage integration to for this textile things to go charge as you go and to real life applications. And the key performance and sustainability target of this GRAPHERGIA things to get a long lifespan, around over 90% capacitance returns and over 50,000 charge discharge cycles. And not only that, the roll to roll scalability, that means is the actively developing fully automated and ambient conditions to pilot line, roll to roll pilot line to the digitally production of graphene onto the text via textile, and also integrate this flexible micro supercapacitor into this textile application. And not only that, this eco-friendly manufacturing of this production of textile production to totally targeting this climate neutral manufacturing steps that fully aligns with the economic this crucial economics this principle, that is one circular economic principle. And not only that, the final applications of the real life application of this smart textile by integrating the energy harvester and energy storage system through this battery-less IoT system and into the daily or everyday clothing to monitor our health monitor system or any other electronics. And not only that, in the aerospace aviation systems system by maintenance free this autonomous monitoring sensor by integrating this very ultra lightweight energy storage systems into the structurally integrable aircraft and aviation systems to go for the say, long lab application. So these are the main approach for the GRAPHERGIA project. And to get to know more information, you all are welcome to visit our online portal and to keep in touch with so to moving on to our today's program. So this is this absolute pleasure for me to give the floor to our first invited speaker, Dr. Professor Rabah Boukherroub, and he will sharing his insight on high performance flexible micro supercapacitor. So please join me to welcoming him. And Professor, your floor is yours, and we are looking forward from hear from you. Thank you.
Thank you so much. I will just share my screen. Okay. If you can just stop the, yeah, okay, perfect. Thank you.
Yeah.
This is okay?
Yeah, now you can put it in the presentation mode.
Okay. Perfect. This is okay?
Yeah, that's good.
Thank you so much for your kind invitation. I'm really happy to be here with you and share some of, I would say, our work on the last few years on graphene based. I was not really initially, I didn't pay attention to it. It's about graphene, but definitely the work I will talk about today, it's really how to make supercapacitors, micro-supercapacitors based on graphene. And essentially two techniques. It will be the spraying and also the laser-induced graphene as well, as I have seen that indeed that you have already a lot of advanced on this topic. So I'll just tell you briefly where I'm coming from. So I work at the Institute of Electronics, Microelectronics and Nanotechnology, which is in the north of France. Here you can see here it's Lille. So it's quite a huge laboratory. It's about 500 people, including, of course, researchers and postdocs, visitors, and PhD students. And it's a technology platform. It's one, there are 5 in France, and indeed, this is the one which is mostly in the north. So we're completely almost, we're in Belgium here. It's a public institution. It belongs to the CNRS and the university. It's a joint unit between the CNRS and the University of Lille. So in the institute, there are 5 different departments related to materials, nanostructures, nanosystems, and macrosystems. Everything is micro-nano, optics, electronics, telecommunications, acoustics, and instrumentations. And there are about 22 research groups indeed working in the different departments. Our group is essentially chemists and biologists. So it's almost half chemists and biologists. And I would say from the chemistry side, indeed, we develop a solution phase often. We mostly focus on chemistry to make materials. And then we add the functionality to these materials through functionalization. So we have really expertise on how we can add the functionality to a very targeted application. That's the reason you see indeed there are different types of applications, either in biology, but also in environment and energy, but also in sensing. Okay, so I started just looking, indeed, if you look at supercapacitors but I was told indeed that most of you, I think, you have already background in supercapacitors, so it probably will just go fast, but definitely it's a very active field. As you can see here, just collected the publications from 2018 to 2026. I'm not talking about patents, just scientific publications from the Web of Science. And it already, you can see there are so many, but from the beginning onwards, it's more than almost 66,000 publications. And the field is quite very active, and you can see still that the number of publications is still increasing. Accordingly, forcingly, you have the number of citations also, which scales up almost the same way. So it's definitely something which there are indeed a lot of to do, and there is a lot of input from the different communities, and you can see more and more I would say, the people are converging towards the integration of all these different, I would say, components to make real devices and very effective and efficient devices. So why in general there isn't, I think this is all of you definitely you know about this, but it's not only this, there's a need for energy storage, because most of our energy today comes from fossil fuels, and that implies environmental pollution, global warming. Unfortunately, you can see now in Europe, 40 degrees is not really usual, especially where I'm coming from, the north of France. Normally at this time we have 25, but unfortunately we're at about 38. So having said that, in any case, yes, energy storage are not just because of this transition. There's a need for transition for more sustainable and clean energy sources, but also for biomedical applications, especially for micro-supercapacitors. And our initial motivation is mostly actually in the biomedical application. I will show you at the end, indeed, what we have in mind, and probably if there are any people interested probably to develop such a, I would say, technology for delivering a biomedical device at the end, I will be more than happy to discuss more in detail. Okay, so certainly, yes, you do as well. You know mostly about the wind, different, I would say, energy sources, which are renewable, but you can only use them when you produce them. Otherwise, you have to store them. That's the reason why there is a need indeed for energy storage. Very quickly, certainly, you know, I will probably, I'm not, you know, the batteries, and today it's supercapacitors, essentially, we'll talk about. Certainly, it's much more advanced technology and effective. You can buy indeed the batteries, you know, all of them. So the advantage of supercapacitors, it mostly comes from the recharge cycle lifetime. You have also a high power density and a long lifetime, but also you can operate that at different temperature ranges, and you can make it from out of really environmentally friendly I would give an example of that on materials, but also on electrolytes. Well, the big issue indeed of the or the limitation of supercapacitors, it's the energy density, which is quite low, and this is really quite problematic. And this indeed, you will see at the end, there is at least some examples now coming where you can combine the benefits or the features of batteries with those of supercapacitors to make hybrid materials, which are indeed combining the advantages of batteries and supercapacitors. And then you can indeed probably, I would say, address partly, not completely, this question whether indeed you can push supercapacitors to the level of batteries in terms of the the energy. So, but it's definitely not the case. It would be something which is intermediate between the batteries and the supercapacitors, but definitely there is a way to go further now with the supercapacitors. Okay, this is just to show an example of how we can use indeed supercapacitors. The history certainly you do know. I'm not going to go through, but essentially what I will talk not about the, because it's graphene or carbon, I would talk about single wall carbon nanotubes and graphene-based materials. So essentially, we'll have these electrical double layer capacitors. So, and indeed, so this certainly is something known, ruthenium oxide, but it's something which is expensive, but it definitely it's an interesting material because it behaves as well as an EDLC. An example here is you see that the fast charging of a bus, which is just takes about 90 seconds, indeed, using these hybrid supercapacitors consisting of activated carbon and nickel hydroxide. Okay, so I guess certainly I will not indeed spend too much time on this, but what's important indeed, if you want to increase the energy, so you have to increase the operating voltage here and the capacitance. Yeah, the capacitance, it's indeed, if you want to gain in that, what we do now with the supercapacitors, you have a high surface area here, but you have to have a very nice control about the pores here, the pore structure, in a way that you can accommodate the anions and cations. Otherwise, you will be just using the surface and not the full surface area. So this is really important when you design a material, specifically for supercapacitors, that you control the pore size in a way that indeed you will accommodate the electrolyte, and that gives indeed much high efficiency. Otherwise, yeah, that's problematic. I guess this, I'm not going to go too much in detail, but this is just a normal electrical double layer capacitors where you store the energy in form of charges. The same applies indeed. You can have what you call the redox active materials or pseudocapacitors, where you have indeed either the intercalation, but also you can have the Faraday materials where you have electrochemical reactions. And the typical one as well in metal, it's the ruthenium oxide, which is also works very nicely as an EDLC type material. That's the typical things when you see, especially for if you start in the field, when you do a typical pure, I would say, EDLC will have this really nice form. If you have some, I would say, pseudocapacitive behavior, then you still have this rectangular with some indeed contribution from the Faradic reactions. And from the galvanic charge discharge, you have very nice, actually, and linear curves. Ideal, indeed, if you have a very EDLC, you will have this linear shape of your GCD. You see there's a difference indeed if you have a pseudocapacitive or a Faraday material, where indeed you see the difference between the two from the GCD, but also from the CV. So this is typically for just to give you an overview when you do the CV or the GCD, indeed what type, I would say, of behavior you would expect from the electrochemical characterization. So what are the suitable electrode materials? Certainly, if you look at the ideal material, I think it's almost impossible to find because, especially when you have a supercapacitor, so you have a porous material, then the conductivity is decreasing. So you need something which would have reasonable high conductivity, relatively high surface area to store as much as possible of charges, something that resists the corrosion, especially when you work in electrolytes. And more specifically, if you're in, I would say, alkaline or acidic conditions, where some for acid, all oxides are not stable, for instance, but also you can induce oxidation even of carbon materials in alkaline or acidic electrolytes. So you would expect also to have a high thermal stability. They can run over a wide range of temperatures. I have indeed addressed this previously for the to control the pore size, something ideal, which is also can make composite materials. So then you can open up to make a diverse materials, should be cheap, ideally biocompatible. It means at the end, especially if you can take just the collectors, and then the ideal that the material could be recycled or it could be biodegradable, then you don't make any harm to nature. I think I would not spend too much time on this because you have certainly the knowledge about the different indeed configurations and structures of the supercapacitors. As I said previously, you have electrical double ADLC, that is a common one, pseudocapacitors, but you can also have asymmetric, where you have either a capacitive and non-capacitive, or capacitive if it's symmetric. But you can also have Faraday capacitive, so there are different configurations you can find in the literature. So often, yeah, the negative electrodes are mostly are carbon-based, mesoporous carbon. That's exactly what you can buy, and it's wearable. They have a high specific surface area, and good conductivity. More recently, there definitely this graphene and nitrogen doped reduced graphene oxide. It's something indeed you can make in the lab. The advantage of this, you have a very good electrical conductivity, but also high specific surface area. That's why you do expect indeed to have a high capacitance. You have ferric oxyhydroxides. They have good conductivity. They're abundant, low cost, but also environmentally friendly. So this is also interesting, but it doesn't feature or exhibit a high capacitance as those you can record from the carbon-based material. For the positive electrodes, you have indeed all, specifically as I showed in the previous example, it's transition metal-based, essentially, and specifically nickel-based. So this is quite available, and it is also used very nicely in electrochemistry because it can sustain really good stability. That is really important compared to many of other materials. So that's why you found a lot of, and also high theoretical specific capacitance. And you can see it here for nickel oxide, which is 2082 farad gram. Now we're talking just about electrolytes. And certainly you do know, if you work with water, what you're facing is the generation or water splitting. It's to generate hydrogen and oxygen, and this is thermodynamically, it only requires 1.23 volt exactly. So it means when you use aqueous-based electrolytes, you are limited by the operating voltage to about 120. Although often I wouldn't say this is really the case, because most of the electrode material, specifically if you use the transition metals, you extend this voltage window, because most of them, they don't exactly behave. Works very mostly for noble metals. So if you use transition metals, this will open up for 1.5 to up to 1.6 before you can start having either oxygen pollution or hydrogen pollution. Nevertheless, when you work in water, indeed, you have certainly a limitation related to this water splitting. So what you can do, you can move to non-aqueous, and essentially acetonitrile, propylene carbonate here. You can see so many of them. So you have a large voltage window, which is about 3.5 volts, but there is always a problem, because most of these solvents can easily capture water, so then you will be running the same problem if you have a mix of water and your organic solvent. So you have continuously to work under controlled conditions in a way you don't have any water traces in your solvent, organic solvent. Interestingly, you have what you call ionic liquids. So are these really basic organic, people call them a green solvent, but they're really not green, because most of them actually are toxic. So that's one has to be careful indeed, depending on the chemical structure and composition. This could be really toxic. The advantage, they have a very large potential window. They're low flammable and low vapor pressure. However, this comes with some limitation, which is the insufficient ionic conductivity, and they're often quite viscous. But I will show later on that there are other indeed alternatives for this, and they work very, very nicely. So just to give you indeed some metrics, I think you do know about what we're going to That's what you get from cyclic voltammetry, or all the capacity or capacitance. Indeed, capacitance when you have an EGLC, but when you have a Faraday type or intercalation or pseudocapacitor, indeed you talk about capacity. So that's indeed what typically you look when you run this, or you prepare electrodes for a supercapacitor. You look at this metrics, but also you look at the stability, and you want as well to reach a high energy density and high power density with something which is very, very stable. Okay. For micro-supercapacitors, indeed, everything the same applies. There is nothing different. But now what you open up, it's indeed in terms of the applications, because you can really target quite large different applications in wearable devices in agriculture, animal tracking, Internet of Things. So there are healthcare and biomedical applications. So this is definitely where I think this micro supercapacitor have the advantage, but also they can be produced, hopefully at least in a cheap and cost-effective way. So I will give some technologies indeed how we can produce this in a very simple and easy way. And it's related also to the some techniques I have seen indeed in the first presentations. Well, there are the different configurations of micro supercapacitors. It's indeed, you can have it's a stack, or you can have one in facing the other. But most of, in our case, we worked on this configuration. We have indeed, because we use laser patterning, so it's much indeed easier to write directly onto the substrate. But we see indeed, in contrast to the supercapacitors, micro supercapacitors, I would say community is not as active as it was. You see, they checked today, indeed, in terms of publications, you have on average 110 per year, but it starts even to decline, so there are not so many. The reason I really don't know why, because probably there are some technological aspects. Some laboratories, they don't have access compared to supercapacitors, where indeed it's much easier to make, especially at I'm talking about scientific level, not at the technology transfer. Yeah, it's a powder form. You make probably a few tens of milligrams, and it's enough indeed to, I would say, finalize a study to make a publications. But definitely on micro supercapacitors, it's slightly different, because you need really, I would say, different technology than just those we commonly use in the chemistry laboratory. As you can see, indeed, the different techniques, I would say here, the fabrication techniques of micro supercapacitors. You have the screen printing, you have the inkjet printing, stamping, spraying, and laser-induced technique. So I will indeed give two examples on direct spraying and laser-induced, but also there is one I didn't. I removed the results, but I can share indeed if someone wants to discuss about how we can combine indeed laser-induced graphene with the spraying to make hybrid materials, where you can benefit from the graphene conductivity and the energy storage of the other material you can spray on top of these graphene lines. This is the history behind the micro supercapacitors. So you can see, I'm not really going too much in detail, but we see it's mostly what evolves. It's the technology and the materials used over the years, but it's still quite recent technology, 2016, we're 2026, so it's about 10 years. It's something which is quite, I think, active field, and there is a lot of room indeed for improvement and for discoveries in this area. So the work today I will be covering, it's a PhD work of Jiahao Wu, the collaboration with Min Li, which also my previous PhD student. Now she's both are assistant professors, she's associate professors in China, and the collaborations with the group in Turkey, essentially for a liquid crystal-based electrolyte to make a all solid state devices. The first technique I will indeed focus in, it concerns the spraying. So in this case, what you need is just, you need a mask. So, and you need your ink here. We took single wall carbon nanotubes, so it's really dissolve them in an organic solvent. It's really easy to spray. You remove the mask and you have your electrode, the positive and the negative electrode. You can see if you do that on a flexible substrate, you can easily deform. So mechanically, it's really, really stable and robust device. So here we applied the jet electrolyte based on this lauryl ether and phosphoric acid. It's like a liquid crystal. And now if you look at the characterization, so we looked at the conductivity of this single carbon nanotubes when you spray them on the substrate. It's quite good. So you can look at the XRD as well. You find the feature of the single wall carbon nanotubes. The same applies in the Raman. You have essentially the G band, but some of the defects, fortunately, because you operate in air. Some of these carbon edges definitely are oxidized, so you generate some defects. And you can see it also by the presence of oxygen in the XPS. But essentially, on the carbon, you see essentially sp2 carbon. Some of the carbon are oxidized indeed on the surface, or it could be also from some contamination. Okay. When you record so we use the two different the PVA and the two different gel electrolytes, PVA potassium hydroxide, but it was also this liquid crystalline based gel. And what you can see, indeed, we can really operate at different temperatures, and also it gives, you see, much higher, I would say, energy efficiency when you use this crystalline liquid. And this crystalline liquid is really easy to make. It's not very difficult. So it's really very easy and simple. So you can achieve really high energy storage performance. So this is just a very simple, like always, if you want to publish something, you have to show a practical application of that. And indeed, what we did is just to put 3 of these devices in series, and then you can open up the potential, the operating voltage. And we can charge the supercapacitors with a small solar cell here, and then we can operate an LED for, I don't know exactly how a few seconds, certainly. But it's just to show indeed that you can charge and discharge, and in a way then you can operate a small device. The second aspect, indeed, it's regarding the laser-induced graphene. So I guess I have seen already a big, on the slides previously, this technique. It's really easy to implement, and you can easy also to scale up. It's very simple and cost-effective. It's tunable because you work with the laser, so you can pattern. You can also play with the laser wavelength, the scanning conditions, the substrate, and all of this, of course, will definitely influence on the structure of the final graphene type material. The only thing indeed one has to say, although we can consider this as very cheap, but also you generate CO2, because all you do indeed, you provide such a high energy from the laser input here, you burn your carbon-based material so you generate quite enough CO2 indeed. This technique was not indeed initially, it was just discovered by, I would say, it was not meant to be for writing graphene. It was the graphene which is deposited on a polymer film. The idea is to treat with a laser to see if you can make much higher conducting graphene. It was graphene oxide, to transform graphene oxide to reduced graphene oxide with a laser. And in turn, indeed, that it happens that there is a formation of graphene under the graphene. So, and that was developed by the group of James Turin at Vrije Universiteit. So then they applied this for almost everything. Wherever you have organic precursor, organic-based polymer, you can write directly with this CO2 laser. You can see in different features, different starting materials. You can even take the potato, whatever you want. You can really use this for making graphene type or graphene-like material. So here we start with the polyethylene. Indeed, it's we use a CO2 laser the same way. You can write your electrodes here, the positive and the negative electrode, the same way by just optimizing the conditions. Then what we did, we just spin coat a PDMS on top of this. You peel off, and then you have your electrodes here are transferred very nicely to your PDMS. And you know PDMS is a flexible material, so you can deform that in different ways you want, and you don't have any problem with the, or you don't lose at least the features that have been transferred onto the PDMS surface. You can see it's not as previously. I mean, you can find the graphenic feature in the XRD, but this time in the Raman spectrum, you can see there is a D band, which is quite actually important, because the way you make the laser-induced graphene, indeed, it's defective because you use a high power and high energy. So it's not like a CVD graphene we have almost, or carbon nanotubes where you have almost no defects. Here at this time, indeed, you're mostly dominated by defects, and you have a lot of edges as well, which are consisting essentially of carbon oxygen. Because it's done in air as well, you oxidize slightly the surface. Fortunately, you can see it with the XPS, but essentially you have a carbon sp2. So now we can see what's important indeed, that the surface looks, it's porous. So this is very important, as I said previously, because then you can indeed accommodate much more electrolyte, and then you can enhance the capacitance and the energy density. Okay. So yeah, you always find this typical, it's not ideal rectangular form, because you have also carbonyl groups on the laser-induced graphene, and those will contribute differently in a redox type energy storage than just an EDLC type. So, but what's important now, indeed, this is the stability, which you keep quite a good stability and high stability. You can deform. Indeed, you can bend to 90 degrees the device, and there is absolutely, we did this up to 1,000 cycles. Of course, you can do this for more, but it's I think it was sufficient for the lab scale to show that indeed you can bend, you can measure the capacitance, and indeed there is no difference before and after, and this keeps indeed for more than 98% of the initial capacitance. The same way we put these two actually devices in series, and then you can, when you charge that, you can indeed up and discharging, you can power this super small calculator. I will go to another example where indeed we wanted to combine the, I would say, plastic recycling with hybrid materials. So we took plastic. This is just PET, so it's the bottle, you know, the plastic bottles. And what we did indeed here, we hydrolyzed this chemically. When you hydrolyze the PET bottle, you generate this molecule, which is then can be combined with the any. Here we use zirconium salt, but it could be any metal salt, and then you can grow MOFs. Certainly, you know MOFs, metal organic frameworks, on the plastic. Now, with the laser, we can transform this. Instead of having what you call laser-induced graphene, you would have a zirconium carbide with graphene. So you have a completely different material, which consisting of zirconium carbide and graphene. Of course, you can have other, if you change the metal here with something else, you will have here either a carbide, the metal carbide, but a different one, but not the same, depend, of course, on the metal used here. The advantage of this, it has a high conductivity, high photothermal conversion, and a good mechanical stability. We didn't do the measurements for the supercapacitors, but I will show you indeed it's very, very nicely conducting material. And one other feature of this work, instead of using a CO2 laser, here we used an LED laser because, again, it's very cheap, it's small. You don't need really too much infrastructure, and the investment, it's just about 50 to 60 euros. And pretty much, of course, you don't have the control as you have with the CO2 laser, but you can do quite enough things at the lab scale. So MOFs, just in case you just MOFs, certainly you do know what MOFs are, just this very nice crystalline and porous material with high thermal stability. They're easy to synthesize, but extremely versatile, and you can store a lot of things inside of it because it's a porous material. So you have quite a lot of applications in different fields. There was a Nobel Prize indeed in 2025 that has been awarded for the discovery of this metal organic frameworks, and you can see here the different scientists to whom the Nobel Prize has been awarded. So coming back to our plastics, what we did, we optimized the conditions, we optimized of the hydrolysis, and we found the optimized conditions. It's sulfuric acid at 75 degrees C for 5 minutes. If we do that, then we add this zirconium salt, then we form this very nice zirconium moth on top of the plastic, okay? This is just, I'm not gonna go too much in detail, but what's important, now that you see there's a small here absorption of this moth on plastic, and the reason why this is important, because we use an LED at 405 nanometers. So the ideal indeed to have, if we can have it here, it will be the optimum. But if we have it close enough, that indeed we can transform this moth layer to graphene and zirconium carbide. So the optimization, the characterization indeed tells indeed that the zirconium is there, the carbon coming from the this organic precursor used to form the moth is there. So everything is there. It seems that indeed the moth is on top of the plastic. And now we use this LED laser. We cannot play too much with because we have quite only two things we can play with. It's the power and the depth. It is not much, but at least when we optimize this, we can definitely make a zirconium carbide graphene hybrid material on top of this plastic. You can see as well we can pattern because it's a laser. And we can initially, when you have the moth, you see the thickness, it's about 6 micron. But after laser writing, you see we have about 145 micrometer. And here the bottom it's the plastic. Interestingly, this material, when you shine light on it, you generate heat. So we can definitely use it for a photothermal. We have a lot of interest in the photothermal materials for biomedical application, for delivering drugs, but also for killing bacteria, especially for anything that is on the surface. We can definitely heat up sufficiently to kit, for example, wound healing or a cancer, which is on the surface. Now, mechanically as well, this is really quite stable. So what we mixed these films with the sand, and you can just rotate that over 24 hours, and you can see definitely there's no any change in the morphology, neither in the photothermal properties or in the sheet resistance. This is really conducting. We didn't push it to the point where you can indeed, and this is ongoing work indeed. Now we want to add indeed a solid state to make a solid state supercapacitor. I will go to the next 2-3 minutes indeed on what's really going on, and I think which exactly where the future of the supercapacitors definitely lies. It's in this hybrid supercapacitor. So if you want to know, this is a technology. It's really, I think, commercialized certainly in China. What's the key advantages of this technology? Indeed, you benefit from the high energy density of the batteries and the high power density of the supercapacitors and the long cycle life of supercapacitors. Interestingly, can operate also this from quite a large temperature window from -40 to +85 degrees C. So this is our examples indeed, which I found again on this company. It's in that they take exactly the known things where you have the lithium ion anode and you have activated carbon on the cathode. So definitely you can improve this by playing here with the carbon. You can, if you can develop indeed very good or much higher effective and efficient materials, I think they're again otherwise, but also this works already very, very nicely. And you can see you cannot reach the energy density of the lithium ion batteries, but definitely can improve this compared to that of the supercapacitor. Okay, so can you see here the lithium ion batteries, the EDLC, the standard EDLC based on carbon, and the hybrid. You see that the power density now it's quite enhanced indeed. It's almost that of the EDLC. But interesting is the energy density now. It's increased, but of course, it will never reach that of the lithium-ion batteries. The cycle life is quite enhanced. The charge time quite reduced. You see, it's only in seconds. And now you can operate this indeed quite over a large temperature window. Okay, so this is definitely something which is very interesting, and also the cost is quite reasonable if you, according to this indeed to this website. I didn't make anything. You can find all indeed the details here if you want to look at, but probably also in some other studies. Another aspect, and I think I will finish, my time is almost over, where is the certainly a lot of things to do today. It's to develop a, I would say, green electrolytes or bio-based electrolytes. And in this respect, a lot of work, at least I would say academic work, is going on using essentially what you call polymer hydrogels or biopolymer hydrogels. And this is in this like chitosan, like a alginate. There's a lot of indeed bio-based polymers. They have a high ionic conductivity. There's not any problem in the aqueous by dispersing them in the aqueous phases. They can be processed very simply. You have also what you call eutectogels. They're based on deep eutectic solvents, or you have bio-ionic liquids. Here you need indeed to do the synthesis somehow or to do the extraction, but definitely there are some things that would contribute to the, I would say, to the future of reaching something which will be much more and more greener and bio-compatible devices. This is the last slide, indeed, when we started this work, what we had in mind, indeed, if we can one day or not, we have developed some patches. It's a patented technology, especially for delivering drugs through the skin or for wound healing. And the advantage of this patch, because you apply just a very small voltage here, it's about 1 volt, and then you can reach a quite high temperature. And this device is based on graphene. And because you have graphene, you can store big amount or can load a big amount of the drug you want to deliver through the skin, or if you want also to treat just the skin, if you have a skin infection. So at the time, what we wanted to do, really, we wanted to have a battery. We wanted to have a macro battery, a micro-supercapacitor, and even we have here somehow energy, I would say wasted energy. We can indeed collect energy from RF waves here and store it in the batteries, or then we can deliver, depending on the application. If you want to deliver a drug, it means you have just to apply a very short pulse. It means you need the supercapacitors. But if you want to do it over time, then indeed you need to have the micro battery. So, of course, we applied for funding. We didn't get funding. So our, I would say, adventure stopped here. But definitely it's something if there is anyone who has interest in this biomedical application of the patches and the combination of patches with energy storage devices for having something which is autonomous, then definitely I would be more than happy to discuss this option. With that, I would like to thank indeed my collaborators, mostly who did the work, and I would like to thank you for your attention. Of course, I will be happy to answer your questions at the end of the second talk. Thank you for your attention.
Yeah. Thank you so much, Professor, for your nice and details informative presentation. It's really got interest to the audience thing. So before going to the next speaker, I would like to inform all the audience that we have a separate question and answering session end of this last presentation. So you can type your questions in the question and answers chat box, or you can ask us in the end of this presentation. So thank you, and I'm now like to welcome our second guest speaker, Dr. Kamil Burak Dermenci, and he will be sharing his insight on the advanced self-healing battery technology. So welcome, Dr. Dermenci, and the floor is yours, and we're looking forward.
Hello. I guess you can hear me, right?
Yeah, we can hear you.
Perfect. Perfect. So now the presentation
Yes,
mode.
perfect. Yeah.
Great. Yeah. Thanks for the nice introduction. My name is Burak Dermenci, working as a senior researcher in Vrije Universiteit of Brussels in the Electromobility Research Center. Today, I'm going to present you some of the our ongoing project. Let's say some of the results from our ongoing project, and I will deep dive into a new concept on the batteries. My talk will be on advancing the self-healing battery technologies through integrated sensing and triggering approaches. Yes. Yeah, the previous speaker already set the scene with a quite a nice way that why we need actually is an energy storage systems. So the supercaps is one of the tools that we use mostly, but also we have batteries, which is quite used in the widespread in all over the world. Since we are living in Europe, of course, we are pushing for a European batteries with a longer cycle life, smart functionalities involved, more safe, high performant, and without excluding the sustainability, eco-friendly manners, and recyclability and reusability. So that is our ultimate goal after all. So actually, this is the point that where Phoenix project arises. So it is as the title says itself, we are building more. We are trying to build more reliable, performant batteries by embedding the sensors and the self-healing functionalities. Also to detect the degradation and repair the damage via advanced battery management systems. So this project is EU-funded project from the Horizon Europe scheme. The consortium has more than 8 partners. We have different partners from all over the Europe, I would say. Fraunhofer, Leclanche, DLR, and Acurec is the partner from the Germany. We are the coordinators of the project and joining from Belgium. We have associated partners, CSAM in Switzerland. We also have a partner in Spain, Cidatec, who is mostly doing the pilot scale prototyping. Communication dissemination partner, Deep Blue, and a co-partner, MWare, which is actually doing the self-healing binder developments. So the project is actually expected to last 4 years, and it is soon to at least we are now in the final push and trying to reach our goal to the end of towards the end of April 2026. So the goal that is that the project funded is from 2022. A little bit more for the project. The Phoenix project actually explores the integrating the self-healing, sensing, and the triggering functionalities into the batteries to prolong their lifespan, and prevent the degradation. So there are different sensors, different triggering devices, and various self-healing functionalities involved in this project. I would say in that manner, the project is pretty crowded. The sensors that we are using at this moment is ultrasound sensors, thermal sensors, gas sensors, the electric elastomer and pressure sensors, and reference electrode for the half cell potential sensing. The triggering devices we are using for this moment is pressure triggering, magnetic field triggering, and the temperature triggering. When it comes to the self-healing functionalities, we have 4 different self-healing approaches. We are trying to equip the self-healing by polymer electrolytes, by binders, by coating on the cathode active materials, or by gas absorbent separators from the metal organic frameworks. So after all, once all of that has been combined, a proper communication between the BMSs should be provided. That will allow us to detect the degradation and to prevent the degradation, to take the necessary actions to avoid that. After all, our ultimate goal is, of course, to build a more sustainable batteries by providing by increasing the QRL, the reliability of the batteries, of course, and with the prolonging the cycle lifetime. So with that, if we can think about the costs, of course, there is also a huge potential to lower the production costs. When it comes to the application of the concept, of course, we have a sensors here, the sensors and sensor signals coming from a single cell, equipped with the different sensors. And then the system is designed to detect if this degradation has been occurred or not. So if yes, then we activate the self-healing and the through triggering mechanisms, and then we try to limit our degradation. If no, we still keep discharging of the batteries. We keep cycling the batteries until the degradation happens, and then the sensors can take their job. So in that concept, for the self-healing part in the PHOENIX, as I said, we have the various types of functionalities that has been considered in a single cell. For example, from the cathode side, we have thermally triggered self-healing polymer embedded surface modified core shell structure cathode particles. So we simply coat with the thermally triggered self-healing polymers with the cathode active materials. We also have the thermally triggered self-healing and in situ polymer electrolyte, which has been placed in the cell. And we also have thermally triggered metal organic frameworks, MOFs, and MOF integrated separators for the absorption, gas absorption, basically, and namely hydrogen, oxygen, and CO and humidity. And magnetically, in the anode side, we have the magnetically and thermally triggered self-healing polymer surface coated by silicon anode. So with that, we are tackling with the cell chemistry with the NMC 990 and the silicon with the silicon. And the oxygen gas capture is also one of the core innovation, let's say, in our project. With that, we aim to capture the water vapor, magnetic triggering, and temperature triggering, and pressure triggering. So this graph actually describes the main degradation mechanisms that can occur in a battery chemistry. So starting from the copper, from the anode side, the copper current collector is widely used current collector. And then we can see the copper dissolution and the dendrite formation after the dissolution. Also, the copper can crack and contact loss between the binder and the current collector can happen. The SEI is an inevitable and indispensable component that actually ensures the long-term stability of the batteries. So the SEI can decompose or reprecipitate during the operation of the cells. So that is also one part of one type of degradation mechanisms. The particle can crack and SEI formation can continue and continue building up, leading to unwanted levels of SEI formed. So that will also have that will also jeopardize the performance after all. Then the solvent co-intercalation and graphite exploration can also happen at certain point. Since we are trying to put the solvents, the larger size solvents into the graphite anode, then of course the graphite could exfoliate after all. When it comes to the electrolyte and the separator side, the most also linked to the anode levels or anode interfaces, the lithium plating and dendrite formation can occur. And if this formation and growth, dendrite growth is larger than we expected, then it can reach to the cathode side, leading to an internal short circuits and will pose safety concerns in the batteries. The transition metal dissolution are on the cathode side, and the dendrite formation can happen. The transition metals and then transition metals can leave the cathode structure and then reform it on the anode side, and then they grow it further to reach and make in the short circuits. The structural disordering can also happen in the cathode crystalline structure, so that this disordering could lead to capacity fades, further capacity fades that is unwanted. The particle cracking during the cell breeding could definitely appear in the cathode side, although it is more cruel in the anode side. The cathodic surface film and the binder decomposition and the contact loss is also other degradation mechanisms that can occur on the cathode side. When it comes to the current collector for the cathode side, the aluminum is widely used, and the aluminum corrosion and the contact loss can happen between the binders and the current collectors. So that also, since there is a contact loss, it increases the internal resistance, leading to a huge and dramatic capacity fade after. In the PHOENIX project, we are basically mainly tackling some of the degradation mechanisms, such as particle cracking and ACI formation, dissolution, transition metal dissolution, and the dendrite formation, and particle cracking. So when it comes to the when it comes to the degradation reactions inside the batteries, PHOENIX project uses silicon anodes. So the silicon anodes are known with the more than 300% volume expansion during the charging, which is quite high. And as a result of this, pulverization and crack formation after the dilithiation. So after the many cycles, you will see it's very small pieces of the silicon, and the further ACI growth will be ACI will be generated on these newly active surface areas. That will of course have a detrimental effect on the capacities, on the performance. So as you can see from the first cycle, the expansion is rather high during cycling, and during discharging, the shrinkage is rather slow, leading to a very huge amount of changes in the thicknesses according to the dilatometry results. So the images below shows actually how crucial it could be. In the initial phases, it's the stack seems all in order, but after the lithiation and the dilithiation, you will be able to see quite a huge and dramatical cracks in the electrodes. On the cathode side, in the PHOENIX, we are using the NMC 90. So lithium, nickel, manganese, and cobalt oxide cathode active materials. So these are oxide-based cathode active materials, and the most one of the most important degradation mechanisms are the oxygen evaluation. So if we can have a look at the oxygen, how the oxygen evolution is happening is actually if we are getting over voltages, or if we are moving the more than the more voltages than it is required, then the oxygen is actually formed. And by the help of the solvents and the electrolytes, electrolyte solvents, they can be further more dangerous to leading to a decomposition of the LiPF6. So actually, water and the oxygen is the most important and most disastrous component in the battery formulation during operation, because it, as said, it also decomposes the lithium salt, leading to a capacity fade, huge capacity fade, because of the reduction in the electrolyte conductivity, and also an excessive ACI formation. So there is one study that shows that the oxygen is actually preferred with this is a computational study, of course, shows that the oxygen is actually favored from the metal oxide cathode material, so it should be avoided during the operation. Degradation monitoring techniques that we use in the PHOENIX project, we have temperature monitoring. Temperature can be, of course, during the operation of the cell, temperature can be generated and it's more even worse in the increased charging rate, and it results in the ACI thickening, and the cells ohmic resistance will also increase. So in that case, the temperature sensor is actually useful to detect the internal cell temperature, especially for the local changes in the cell temperature, to avoid and to prevent the thermal runaway of the cell. So these are some of the images that how we use the temperature sensors in our project, for example. Another degradation monitoring techniques could be the dilation monitoring. So the dilation is basically related to the volume volume changes of the cells. So thanks to these dilation sensors and the appropriate sensors, we are able to monitor the volume changes after all. So this is the design that we are using in our project. The two rigid plates that was placed in between, the cell has been placed in between these two rigid plates, and also with the dilation sensors, and the electric elastomer sensors shows in the left-hand side. And we were able to capture the volume changes of the cells. Another example for the degradation monitoring techniques is ultrasound monitoring. So electrode defects and volume changes can be monitored based on the time of flight of the sound. So we have simply two ultrasound transducers, one's on top, one's on below. So if we are able to align them appropriately, we simply measure the time of flight of the ultrasounds here. And this will give quite a lot of information about the electrode defects happening inside the cell and the volume changes. Another monitoring technique is the gas generation monitoring. Based on the generated gas amount, the gas transfer resistance is decreasing. So this also prevents the electrolyte leakage and the thermal runaway. So as said, the gas is not wanted in the battery chemistry, so we have to detect them and we have to remove them if possible, but it is also inevitable because that is a part of the chemistry underneath. Therefore, we placed our gas sensors, gas monitoring sensors just next to the cells, so that if there is a gas generated between the stack, we will be able to capture it. And after the sealing, there will be that's the PHOENIX way on how we capture the gas. So far, we have discussed on the possible degradation mechanisms, and how the degradation can be monitored and diagnosed in the cells. So now it's the time for the self-healing and self-healing mechanisms. PHOENIX project also uses the self-healing polymer self-healing mechanisms by triggering approaches. Of course, the self-healing can be done in autonomous or non-autonomous ways. So for example, the autonomous is actually based on the self-healing effect that is not relying on an external push. But the triggering as an external push can also be done to trigger the self-healability in the cells. So the use of self-healing polymers in the battery applications appears to be more challenging than a compared polymer self-healing alone. That is the primary outcome of our project, basically. And the pouch cell casing and cell environment restrict the freedom to use the certain triggers. That's also one of the challenges that we are facing at this moment when it comes to the self-healability. The previous project that that was involved in the autonomous self-healing, we were able to establish a candidate for the self-healable binders that could be an option for the silicon-based batteries. So we have used the different binders, PVDF, very much well established in the lab scale research for the NMP-based slurry preparation. CMC and SPR is pretty much widely used in this water-based slurry treatment, and our self-healing polymers. And the results show that if we can tune the content accordingly, the benefit will be remarkable. And after the cycling of the cells, we could see that the self-healability is also taking place, and we were able to see the interlinks between the correct regions thanks to the self-healable polymer binders. For the thermally triggerable self-healing polymer coatings, so we have also conducted this test within our project. So what we've observed is actually a negative effect of the heat. So we've prepared different cells with the, as you can see on the left-hand side, with the silicon without the self-healable properties and silicon with the thermally triggered self-healing properties. All of the tests has been done in the room temperature or 45 degrees. So if we have a look at the room temperature tests, the self-healing and the no self-healing cells are usually having a better performance than the ones on the room temperature. Sorry, the better performance than on the high temperature. So that is actually a reverse and negative effect of the temperature, so that our polymer coating might be much more useful at a lower temperature. So now we are testing the similar cells at 5 degrees, and the results also show that there is a certain amount of improvement in the capacity fade after all. Of course, these tests has been done in a continuous temperature, like 25 degrees at the room temperature or 45 degrees in the climate chamber, with all of the duration of the time of the testing time. But we are also curious about testing this interrupted way. So every 5 cycle, we tested the cells at the room temperature, and every 5 cycle we heat it up to 45 degrees, and then cool it down, and then continue the testing to see if there is an effect on self-healability in terms of the electrochemical results. The results show that there is a continuous decrease in the capacity fade as expected from the silicon cells, of course, and you will see from the Coulombic efficiency drop the exact positions that we applied the heat treatment. But in that case, we don't see any visible improvements on self-healing effects in the electrochemical performance. After that, these were the results for the silicon and without self-healing. When we applied with the self-healing polymer coatings on the tests, and still the capacitor retention is quite similar to the ones that without self-healing. So the results are basically doesn't go to a meaningful levels. And then the synthesis and the characterization of the magnetic triggerable self-healing polymer binders. So that is also one part of the project. Here we synthesized a magnetically triggerable self-healing polymer binders. And in these binders, the characterizations has been done from the by using NMR, FTIR, and TGA analysis. And afterwards, we've prepared a cell out of them, coin cell level, by using the 100% silicon, 20% self-healable binder. And then the EIS, we've performed an EIS, CV, and EIS contribution, or let's say testing conditions. So to see the effect of the magnetic nanoparticles. So in the first, on the left-hand side, it is the cell. The EIS results are coming from the cell, fresh cells, before performing the CVs. So it is a comparison of the PHOENIX polymer and the PHOENIX polymer of the plus magnetic nanoparticles embedded in it. So it seems that the magnetic particles has led to a lower internal resistance, which is pretty much promising for us. And after that, we have performed CV tests up to 10 cycles. The most important point here in the CVs is that in the beginning of the cycle life, let's say, the cells are performing, the cells with the magnetic nanoparticles are performing better than the others. But after 10 cycles, the results and the reactivity of the cells are more or less similar. So they are performing quite similar.
Yeah,
Yes.
sorry, Dr. Dermenci.
Yeah.
It would be good that you can finish and that people can have
Sure.
some time to discuss with you.
Sure.
Yeah, thank you.
I'm coming to the end, actually. Yeah. So we have actually, after these tests, we have performed some magnetic triggering. So here you will be able to see the setup, the experimental setup of the magnetic triggering and how we apply through our triggering devices and the sensors. So it's just a video. I'm not sure if you can hear it or not, but we can move it to save some time. So that was my last slide. So the challenges and the lessons learned in the triggering and the self-healing activation for the silicon anodes, if I can wrap up, the triggering parameters should be selected wisely. So the parameters, these are really parameter affected and parameter vulnerable mechanisms, and we really need to investigate more on that. The irreversible degradation of the silicon nanoparticles actually makes the self-healing effects even harder. The destructive formation conditions should be also avoided. And even though the material demonstrate self-healings physically, as we showed, the healing kinetics and the rates should also be considered to really reflect the self-healability into the electrochemical metrics. With that, that's end of my presentation. I thank you all for your attention. So I also thank especially to my colleague, our PhD student Emre, who helped me quite a lot for preparing these presentations with the results.
Okay, thank you very much, Dr. Dermenci, for your nice and detailed presentation about this ongoing project work.
Yes.
And thank you very much. And now it is open for question and discussion. So I can check, and I'm also open to all audience. If you have any question, I think you can also ask something. Okay, I can see some questions. So first question comes to me. So okay, so what are the challenges graphene-based micro-supercapacitor for implementing PACE application? Okay, so we all know that graphene is very promising material for some supercapacitor, but I can share my practical point of view for because when we apply for the PACE application, we need to integrate the supercapacitor, whatever the spouse shell or micro-supercapacitor in the structures. After structure integration, sometimes we found that is a performance decrease, and we cannot we achieve sometimes for it some cells gives bad response or bad performance in the structure after structure integration. And for the space application and space things, you all know that all device need to work in the quite extreme conditions of the temperature and also the vacuum pressures. And this time the main questions comes on the environmental survivability of this device. And due to this kind of issues, sometimes it makes problem of the increase of self discharge rate, and also giving very low or capacity performance and low cycle life performance. So these are the main things. But that Professor Rabah Boukherroub already explained that people are also interested in the hybrid supercapacitor, and also working with different electrolyte to solve this kind of challenges. So these are the things. I hope I can give you some insight of this answer of your questions. And another, the next things to Professor Rabah Boukherroub, that's how thoroughly research are liquid crystal polymer gel electrolytes right now. Would they be interesting for battery application, and could the system be directly adopted? So floor is yours. You can answer.
Yeah. Well, thank you. Yes, indeed. All the research on liquid crystal polymer is not as active as it is on the polymer gel or deep eutectic solvents or epitector gels. So it's not as much right now, indeed. So the reason I'm not sure whether it's really much more difficult to form liquid crystals, or because it's certainly much easier to work with polymer gel electrolytes, because the polymers you have access to, it's easy, and it's also very easy to form gels. The gelation reaction with the polymers, it's very, very simple and easy. So on liquid crystal, it's probably slightly, we did, the example I have shown, indeed, was not done by us. It was developed in Turkey. It was from the colleagues in Turkey. So we don't have any, I would say, expertise in liquid crystal, at least polymer gel formation or preparation. But definitely, yes, you can apply this as well for batteries. Indeed, it just has to be much more specific. But yes, definitely, whatever you can often develop for supercapacitors or the opposite, yes, you will go both ways, yes.
Okay, thank you very much for your answer. So if audience have any other questions, any comment, just go ahead. You can also type in the systems. And maybe I have just a short question to Dr. Dermenci about the self-healing functionalities of the batteries thing. So I would like to know this what kind of challenges we can expect after integrating the systems, and what is the your expectation to go for this next 10 years or 15 years about the battery technologies, about your research things?
Yeah, thanks for the question. First of all, yes, the challenges are, I would say, can be categorized into different things. The first one is technical challenges. So the technical challenges, the responses basically, I mean, the most important challenge is the response, the electrochemical response that we got is not in the level that we want. That is the case for the triggering systems. For the autonomous self-healing, that's I would say it is more promising, because after all, it happens automatically, autonomously. So you will be able to see a clear difference in between the non-self-healing, or if you want to introduce a self-healable binders. But with the triggerable systems, triggering conditions are really playing an important role out there. So the technical side is there. Also, when it comes to the sustainability part, most of the sensors we are currently using are critical raw materials. So we should bear that fact. They are expensive. They are not environmental responsive, let's say. Therefore, there is also a need to search for an alternative sensors and the triggering devices to be integrated into the cells. But after all, the benefit is there. So if we can monitor the degradation during the cell, we won't be able to see the issues with the ones that we already face in the electromobility sector, like cars are getting firing or anything. I mean, there are quite a lot of opportunities can be built if we are really reliably diagnose the degradation and to recover them.
Okay, thank you very much for your explanation and nice answers. And I couldn't find any other questions to be answered, so I think I would hand over to you, Mona. You can finish this webinar series. And thank you all of you, all attendants. Yeah.
Thank you, Apurba. So on the behalf of the GRAPHERGIA project team, I would like to thank all our 3 speakers today for this nice session, and specifically thank all the participants. So this session is indeed recorded and shared with all of you after in our communication channels. So a warm thank you, everybody. I'm just stopping the recording.